Hello, everybody. Welcome to the third episode of the CSGS talk series. Today, I have the pleasure to introduce Bettina Kemme, who is an associate professor of computer science here at McGill University, where she leads the Distributed Information Systems lab. Her research focuses on large-scale distributed data management and system support for data analytics. She has published over 100 publications in major journals and conferences in the areas of both databases and distributed systems. In 2010, she won the VLDB 10-year Test of Time Award. She has also participated in several European projects and has served on the program committee, as well as area chair of major database and distributed systems conferences, as well as editor for the Elsevier Information Systems journal. She's also a senior IEEE member. So without further ado, hello, Bettina.
Okay, thank you. Can I suggest, can you give me to share the screen? Is this possible?
I think, yeah.
Okay, let me see. Here we go. And I'm not quite sure. What do you see right now? Do you see the whole presenter view, or do you see?
No, we see your presenter screen.
You see everything, or just see the first slide?
Everything.
Okay, let me take the other one in. Let me see. What is this? Play from start. Here we go. So that would be better then?
Yeah, that's perfect.
Okay, cool. And I have to look at the watch for the timing. Okay, so, well, thanks for the introduction. As Loic said, for the last 2 decades, I have worked in a database and distributed systems, and I want to give you a little bit of flavor of what it is. The area has been moving quite rapidly. Like 15, 20 years ago, it was really hot because Google and Facebook and Twitter, they came all up, had huge amounts of data, had huge amounts of data processing tasks, and basically the systems community was also really there to build the platforms, to create the cloud infrastructure, the distributed platforms for execution for all these large-scale data processing. So this was then established. The big companies took over, and the research field has moved forward. And I would say in the last 5, max 10 years, obviously with machine learning becoming more and more important, it also greatly influenced the area of systems. And I want to bring a little bit of overview of what is going on there. And there's 2 aspects to it. Just like in any other domains, the systems people ask themselves, can we use some of the machine learning tools to make our systems better? And that's machine learning for systems. But on the other hand, if you look at machine learning, it's large scale data processing systems by themselves. They feed in data and then they do a lot of processing and something should come out. So this should be done efficiently and fast, etc. So obviously there's also the other aspect that you have to build systems to support machine learning computation. And so I'll try to give, the first one will be a little bit longer, but kind of give an overview of both of them and then show also a little bit of how my work is reflected in that. So the background is if you want to build large scale support for large scale applications, the work by itself, I want to give a little bit of flavor of also how you perform distributed systems work. On the one hand, you try to find the problems, you develop high-level algorithms on it, but then at systems work, you really build the prototypes, you evaluate them and see how they work. So one example, which has been the classic example and driving a lot also research in distributed systems is e-commerce, like your big Amazon and the other stores that came up. They typically follow a distributed architecture where you have different components that communicate with each other. You want to do this modular from a software engineering point of view, but you also need this distribution for reliability, for scalability, for efficient execution. Typically what you have is you have at the end some database backends that do the data storage, you have caching systems, you have components that implement the business logic. So you might have to distribute the tasks for load balancing, but or you replicate, you have several instances of the same component for scalability, but you might also want to replicate because of fault tolerance. So I have been working in this area in particular with replication for a long time. And so with a time, have been moving more to cloud infrastructures. And one of the components where my student Mona has been working on is when you have these large scale distributed applications that run in the cloud, you want to monitor them. And what comes obviously immediately into mind as well as performance monitoring. What is the throughput, the response time of each of these components and the components as all? But there's also other important aspects. So for example, if you are a cloud provider, an administrator, and you have something running in one of the virtual machines on one of your nodes, it might be interesting to know, well, which other components does this component access? And then recursively, which other? So you kind of want to build the application graph, as you see here, for example, in this left picture, given one of the components. Can I create this entire graph of components with which this component interacts? Because this will help you monitoring the entire cloud application. And not only that, I would also like to know what kind of services then each of these components provides. Is it a MySQL database? Is it a DB2 database? Is it a cache? Is it a web service, etc.? So there are all kinds of different things that you can understand with monitoring. And that doesn't hold only for these distributed component-based applications, but also I saw Juana has given a talk. I don't know, I'm sure she talked about key value stores. Maybe she talked about distributed key value stores. You have these large processing frameworks like Hadoop and Spark that do complex distributed computations, and you might want to have exactly the same requests to perform this monitoring. And so Mona's research was as well, can I perform this monitoring, build a monitoring as a service system that you don't have to do anything with the individual components. You don't have to put anything on the host. You don't have to instrument your components. You do everything by just observing the messages that these components exchange. And you do the monitoring in the network itself. So for example, if you have your cloud network, obviously it consists of a lot of switches that kind of forward the messages around in the cloud infrastructure. Can I attach components to these switches that sniff the messages and do all this performance analysis? So on the one hand, so there's a lot of systems aspects to solve. So obviously some more lower key things is since these agents that we call here are attached to switches, they have to have a lightweight execution. They have to have a small memory footprint. How do I implement that? There's algorithmic questions to answer. Obviously, they are distributed in the system. They will communicate with a central controller. How do I perform the coordination between these components? How do I do the data collection? How do I do efficient and communication with a low extra overhead? So these are more the systems aspects. And now I just want to bring, how does machine learning now kind of play a role in a question like that? Now, one of the things that I brought up was the question of, given the communication between two components, one being the client, one being the server, and this, for example, being a MySQL database system, how can I determine just by looking at the messages that this is a MySQL database system, or that this is a DB2 system or a Redis server? How can I determine this by only looking at the messages? And so this has been a well-known problem. And there have been all kinds of, oops, I haven't put I should put play from start. What's here? There have been all kinds of solutions to it. So the standard format, there's no machine learning, nothing in place. So what you would do is very straightforward. Well, you have a communication protocol. The endpoint in an HTTP web service communication protocol is always 80 or 80/80. So if I look into the message and I find this as an input, I know this is a web service. If you have dynamic ports, which you have quite often, well, then for those services, this doesn't work. So what you could do is you could do a deep packet inspection. You really go deep in and you know exactly what is the message format of a MySQL database, what is the message format of a Redis server, and you compare them, and then you look at the messages and you determine, okay, that's a Redis database. But that's of course very cumbersome. You have lots of complex rules, so also not ideal. So then comes machine learning in it. And then the first thing, you can take traditional machine learning algorithms, and the ideas that came out there was, well, I have a message flow that's basically a sequence of messages, and I try to collect some features about the characteristic of the sequence of messages. So for example, what is the inter-arrival time between messages? What is the typical average message size, etc. And I build a feature vector and I feed it in these classical machine learning algorithms. However, the feature engineering is still quite tedious to find exactly the features that might be beneficial for then determining what kind of service it is. And very recently, there have been some proposals to actually use deep learning approaches. And so again, deep learning approaches are, for example, good for language processing. You have a sequence of words and you understand the meaning of it. You have a sequence of images. You do a video analysis. So what we could do is we have basically, look here, the messages that are exchanged between two components is a sequence of packets, and we consider this, for example, to be an image or a time-based sequence of data, and we just basically transform this into something that a deep learning model can understand, and poof, it learns. So we have looked at a couple of the proposals and compared them, and have also investigated some different deep learning models by ourselves to see whether it works. And here's just one of these examples. So those of you who are familiar with machine learning algorithms, these LSTM deep models are often used for language processing or for sequence-based video analysis. And basically you have a multi-layered system, and the lowest layer, what it takes, each of these components would take, for example, an image as an input, and as total, this gives a sequence. So what we can do is we make each of the package an image by taking, for example, the first 30 bytes of the package and translate each of these bytes into a pixel. So boom, all of a sudden your packet is an image, you have a sequence of image, you can feed it into the model, and with this, learn it. And so we have tested all kinds of different possible models, and as a good systems work, so if you try to do it, obviously you have to give the model a large training set. So we have built a lot of example applications that use a wide variety of database systems like Postgres, MySQL, DB2, MongoDB, Cassandra. We have used a couple of caches, a couple of compute frameworks like Spark. We have built application traces for it. We have fed them into these machine learning algorithms and looked how good the performance is. And performance in machine learning meaning accuracy, precision, recall, etc. And here you find one of these common performance metrics as the F1 score. And we can see that, we just take a standard algorithm that is used for video analysis, and it works astonishingly well, just simply to detecting service types for network traces. And you can see for a lot of these services, the F1 score is by far higher than 90%, which is really an excellent result for these message traces. A lot better than a lot of the other proposals that have been proposed so far can do. And they do this without, you can just feed it in. The advantages that you don't need experts that would understand the communication protocols, etc.
A little question here.
Yeah.
I'm just wondering, so is this for each kind of different service, it's binary classification, either it is of that service or not? Well,
you get basically a flow, and yes, it's let me say, how was it done? Mona is in the talk. I think she can give the explanation, but it would basically split out exactly one of those. It's a multi-class classification system.
Okay. Yes, but I think for the question, if you are considering for a specific service type, yes, it is a binary classification. So for each input, you are if you are considering one service type, you are saying if it is belonging to this one or not. But now we have a multiple services, so it is a multi-class classification problem.
Okay, thanks. Okay.
So this is just one example how you can use machine learning for assessment tasks that we have done in our lab, but obviously there's a lot going on, and I want to just give you a little bit of insight of what other people have been working on. And I will focus on database systems. Why? Because I assume most of you have taken the database class, and so you would kind of know more or less what a database system was doing, if you can still recall it. And you will know that a database system is a complex system consisting of a lot of different components. You see here, I just took this figure from the web. Queries come in, you have a query processor, you have an optimizer who builds an efficient execution tree. You give it to the scheduler who decides how many queries they want to run in parallel. You give it to a transaction manager to guarantee consistency despite updates. You access your data through a buffer manager. All your files are on disk. You have to retrieve it. You have index files for faster execution, and. So there's a ton of different components that make up the database system. And now the question comes, can machine learning help to make the system overall better? And so the last 5-10 years, lots of research groups have started to dig into the different components. And I just want to give you a kind of an overview, an idea of what problems could be solved with machine learning, and people have tried to tackle this. One important one is knob tuning. If you have ever installed a database system by yourself, you will know it comes with a huge configuration file where there is tons of different parameters that are given default values, but you can change them so that the database system runs better for your application and your workload and your data. Well, how do you know which one are the best parameters? Now, if you have a very expensive data administrator on hand, and there are a few around, they will look at your application, will have a gut feeling, and then will adjust some of the parameters through 20 years of experience working with database systems. So that is obviously not a very effective way of tuning your database, or you try out yourself until you find the right configurations. The question is, can machine learning help you with that? Another example is, you might still remember that you can have secondary data structures like indexes that will speed up some of your queries. You might also remember that a lot of databases support some form of distributed data so that you can split your tables into several ones so that you can do some parallel execution. But how do you partition your data? Which indexes are you going to generate? Again, your system administrator will look at your application and will hopefully find the right indexes for you to create. Another question is, when a query comes in, you might know that the database system has many different ways to execute the query. So what it does an optimizer, it explores many different execution plans, and then hopefully finds the fastest of them to execute the query. And there's a lot of things of how you can rewrite the query, etc. So again, this is an NP, all of these are NP hard problems, and researchers have started working and trying to find machine learning solutions to that, so that you just model your problem, put it in the machine learning, and it spits out the right answer for you, which parameters, which indexes, etc. So anything that you know from your machine learning course in terms of algorithms has been tried out, just simple regression mechanisms, gradient descent-based ones, deep learning, reinforcement learning, deep reinforcement learning. So everything is right now being played around to see what it works. The challenges here are that large training data typically, particularly if you want to have deep learning models. And so if you're a researcher and you think, I think this model will really work, well, you need a lot of workloads, databases. Well, how do you get this data? Just as Mona had to collect a lot of traces, this year is even more challenging. Generating gigabytes of data is a very challenging task. If you are a company and you are Oracle, a database company, maybe you have a better luck because you might be able to use the data of your customers, but as a researcher, it's a harder time. After that, obviously, the question is the feature extraction. You have a query execution plan. Those of you who might remember, it's kind of a tree that shows all the different operators that you have in a query. Well, how do you translate that into a feature vector? It's not a straightforward task. And this is similar for other ones. How do you translate this into something that you can feed into a model? And another problem that arises is, well, this is all very dynamic. How can you provide dynamic model updates, for example, to handle changing workloads, etc.? So these are just some of the questions that have to be handled by these new systems. Another interesting research that is performed in this area is changing data structures. So hopefully all of you remember the very famous B+ tree, which is the most known data structure, a secondary data structure that you have in a database system. So it helps you to perform, so you have your database table, and it helps you to perform certain range queries on the database table. So assume you have an attribute in your table that is a score, and you want to have all the records that have a score between 5 and 10. Well, how do you find them in the core data is you go through this through the system, and you tingle down the tree to finally find the entries in your data that you then afterwards want to retrieve. So it makes the search logarithmic. Now, what you find here in these inner nodes are typically lists of values, and you have to find the right value. And then there is an arrow, is a link to the next the child, and you follow that to the next child, etc. So here, an idea that came up very recently is, instead of having these very well-defined structured lists that guide you down the tree, you put a learned model in it. For example, just a simple linear regression model. And then when you look for the value of 5, what you do is, here is just a model. You perform an inference of the model, and the output is the child that you should follow in the tree. So instead of having lists in the inner nodes, you have a learned model and you perform inference when you travel down the tree. And it turns out super effective. Lower storage space, faster execution time, a very impressive result. So obviously this is all still preliminary, updates are not handled properly, et cetera, but as a starting point, this is something quite amazing as a completely different solution to what exists so far. So in summary, there's many ad hoc heuristic solutions that are believed that they can be replaced with machine learning solutions. And the cool thing is then that you don't need database expertise anymore to tune your database. The success of these things is to show that the potential of machine learning to lead to a major rethink about core data structures and functionality that are used in systems research. But to find the right solutions, you need people who are experts in machine learning and in systems, because there's a lot of low-level details that have to be handled. Often the machine learning algorithms cannot be taken from scratch. You might have to adjust them to your needs. So it's a challenging area that needs a lot of expertise. So with that, I want to come to the second part, and that is how to build systems for AI. And again, I had a student, Joseph De Silva, he's now a faculty lecturer at the school, who has looked into this during his PhD thesis, and we are still working on this tool together now with a lot of undergraduate and other master students who enhance the tool. And here's the basic idea. Actually, most of really valued data currently resides in relational database systems. According to our survey here, actually 65% of the data that is used by data scientists reside currently in database systems. These are powerful engines that have very good execution for anything that looks like a SQL query. However, not just simply run a Python data analytics task on this data. So what data scientists currently do, they take the data out of the database. For example, I don't know whether you have worked at it in data science tools like pandas, just to a Python program, maybe into TensorFlow programs, etc. Or if you have a lot of data, you take it out and you load it into your Spark cluster to do a distributed computation with frameworks like Spark. But in all of the cases, you take the data out of the database, and then you conveniently work there. You have this concept of a data frame, which kind of looks like a table, a multidimensional table. You perform your matrix multiplications on it. You can still do some selections, etc. on it, but not, of course, you have the power of programming languages like Python to program your problem. So you have a convenient programming paradigm, but you have this huge delay out of the data, out of the database system. And with a lot of, you cannot use the database system and all the relational power that the database system has, you cannot use it anymore. So the idea of the AIDA project that our lab has done is that instead of taking the data out, we push the computation into the database system. So we take a database system, we embed a AIDA server into it, and we have at the client side a standard Python interface or a Jupyter notebook or a Pandas interface, and you make your calls in your Python program as you have done it before. But whenever you want to execute something, you actually send it via a remote method invocation to the server side, and all the data is retained in the server, and the execution happens there. So you have a client-server architecture. You write your programs just like you used to do it. You have a thing that's similar to a data frame. In AIDA, it's called a tabular data object, but the data resides at the server side. You only get here stubs that look to you like the data, but they are actually not the data, so you don't take anything out. And you can do all your transformations here. You can do your Python programs as you like, but the actual computations take place at the server side, either in NumPy when you do linear transformations, or on the SQL engine if you do relational transformations. So it's very convenient, but as convenient as data science frameworks, but it is as performant as relational database systems and large-scale server systems are. So with this as a starting basis, so this was kind of just a first idea of it, and we have been working on it a lot. And some of the work we are doing right now is very similar to what other research groups do that do systems research for machine learning. So one part where systems researchers work a lot on is supporting better GPU support. So most of you might know that machine learning algorithms work actually quite well on GPUs, because they process the same instructions on a lot of data, and this can be done in parallel, and GPUs are really good with this. And you have, as a data scientist, you might use TensorFlow and it does the work for you. So that is great, but maybe you can do much better. We have done some analysis and turns out TensorFlow, I don't know, we never managed to get more than 30% GPU utilization by using TensorFlow. So by really knowing better how your architecture works, you can get more out of your machines. And you can see this, I'm not going to explain this figure, that the architecture of how the CPU communicates with the GPU, where they are all memory caches and how the memory caches interact is not straightforward. So if you have a particular deep learning problem, questions arises. What should you execute on the CPU? What should you execute on the GPU? When you have several GPUs, how do you distribute the work over the GPUs? Do you perform a pipeline? Do you do kind of a different kind of distribution among it? So it's kind of a distributed machine learning in the small, it's a single node, but you have many different compute resources, and how do you use them the most efficiently? It's impossible for me to give a talk without having one serious performance figure. I cannot give a systems talk without a systems performance figure. So here's one, very easy to understand. So we just have tried in AIDA, what is happening if we run database queries on the database part of the system and machine learning algorithms, which are very CPU and compute hungry. If you run them in parallel, how does the machine learning algorithm affect the query processing? And you see here on the left, time passes here on the x-axis. We have queries that are continuously submitted to the system. And then at time point, and you see here the response time. And then at time point 2, we start a machine learning task, and we run both the queries and the machine learning tasks on the CPU. And you can see how the response time of the queries is super negatively affected because the machine learning task takes over most of the resources. While here on the right-hand side, we run it on the GPU, there's still a negative effect for the query, but not so much because we are able to handle most of it on the GPU, so there's not a negative effect. And I just bring this obviously seems like very straightforward. I just mentioned it. This is how we wanted to start to understand how they interplay. Just building these two pretty straightforward results, I think, took an undergraduate student a good 2 to 3 weeks of installation, getting to run it, setting up the configuration. So if you do research work, you know, these graphs that you see in research in our research papers, they're really hard-earned graphs. And Mona will be able to tell you more about any of the individual graphs that she has produced there. It seems like the machine learning graphs were a lot faster to generate than these tasks on performance issues and distributed systems. So just the last topic that I want to tap, and I talked already about the GPU, CPU processing, is something of distribution. Obviously, you can also run your machine learning task on a cluster of nodes if you have very large scale execution. And obviously, this is very to my interest because I'm working in distributed systems. So I looked at a survey about distributed machine learning, and I found those figures in the survey. How you could run a machine learning algorithm in parallel. Again, what the machine learning algorithm does, it feeds in a lot of data and then performs some computation. So what you can do here is you can partition your data. You have different compute nodes, and each of the compute nodes gets a little bit of the data, performs part of the machine learning task. Then obviously you have here an assembling where you have to coordinate and aggregate the information. If this might become the bottleneck, then you can perform a hierarchical distribution of this with a nesting in form of a tree, or you have here at this level several of these servers at the highest level that communicate with each other, or you can have a peer-to-peer system here where each of the nodes communicates with the other. So all kinds of different architectures of how you can distribute your machine learning task. And when I looked at it, I was stunned because I have a very similar picture of that in my distributed systems class that I teach in the fall semester. But there it was, I think, about distributed database systems. And it's exactly the same architecture. It's why you have a lot of data, you have processing, and these are the possible fundamental possibilities how you could distribute it. And you find now in the machine learning algorithm exactly the translation to machine learning algorithms of these ideas. And just one to mention that I find quite interesting is that machine learning algorithms have two kinds of data. They have the data that they feed in, their learning data, the training set. But if you look at the deep learning model, it has a lot of parameters, which are the weights of your machine learning functions. And if you look at deep learning models, they can have hundreds and thousands of these parameters. That's also state. And that state changes continuously during the learning process. So if you know a little bit about transaction, you have your e-commerce site at Amazon, your data in a production system like this changes all the time as people buy new data. The data is continuously updated. And these systems have worked a lot already with replication, with distribution for reliability and scalability. And so they had already mechanisms in place that if different nodes want to access the same data, how do you do the coordination? If you want to replicate data for scalability, how do you keep the copies consistent? So there's a lot of consistency protocols being developed. And the question now is started, can you adjust the solutions that you have developed there for this new debate? So if you look, for example, at TensorFlow, it uses this parameter server, and its performance is actually really bad in its original version. So can you apply new mechanisms to it to make, for example, this parameter server architecture more efficient? And there has been quite a lot of work just in the last 2-3 years on this topic. And with that, I want to summarize. So it has been a very active research areas. Currently, the solutions that are explored are more point solution. People look at one specific small problem and try to solve. For example, can I do a workflow-based CPU, GPU distribution for graph-based deep learning models? And how do I now adjust the cache for this particular problem? But obviously, these solutions have to be eventually generalized, and you have to build the frameworks that embed the most important ones of them and then deploy them whenever problems like this come up. So there's still a lot. So for example, there exist frameworks like TensorFlow, but I think there is a lot of potential to make, to integrate more solutions into them to make them more efficient. And for machine learning for systems, so a lot of solutions have been explored so far. They are not yet generalizable, and very little has so far found their place into production systems. So once this happens, it will be interesting to see whether in real life the performance is as promising as you find right now in the research papers. And with that, I finish the talk, and I'm happy to take questions.
Thank you very much for this great talk. Yeah, so we can open for questions now. You guys can post it in the chat as well if you want. I have a couple questions. Maybe I can start off.
Yeah, sure. Go ahead.
So, I mean, one thing that I thought was interesting in the learned indices, so you said one of the biggest successes of ML for systems. You mentioned like they don't currently handle updates. And so I don't know if you can talk more about that, because yeah, it seems if you're going to be using like some kind of machine learning, then it seems like you'd have to retrain the algorithm every time there's an update, to be able to adapt.
So some of them can handle updates in the sense of, for example, let me go, you have to do smart things of, so where did I have it here? Oops, no. It's here. So, I mean, it looks, updates in the terms of you can put new tuples here. Yes, that can be. Where the tricky thing is, if in the inner nodes you have a learned model, if your distribution remains the same, whatever you have, independent distribution, there's no skew or whatever, then the learned models will stay the same as you enter more and more data into the system. But if you get skewed data, then you have a bigger trouble, because then you would have to relearn your models. And so how do you relearn your model? So if you split, so for example, you have a learned model here, and you have a learned model in another node, and these models are different, but now you have to split the tree because it grew. And now how do you do the relearning of these individual models? So yeah, there's definitely, it's right now in the process. It's kind of not 100% solved. I just basically reviewed a paper on that that was submitted now that tries to solve this problem. And so I wouldn't know now exactly how individual solutions would solve it, but I think it would be partially solved if you can also have models. And I think this exists in the machine learning world. You have learned a model with certain data, but now your data changes, and you try to hope to adjust your model to drift a little bit according to the new data. And so what systems do is they try to generate of the new data to feed it quickly to the model and to basically adjust it to the new value. So these would be, for example, approaches that you could put in there.
Yeah, the
that
online
is just
machine
one suggestion, and one would have to see maybe smaller models, and then you can replace individual models faster. So one would have to think about how to adjust it. And as I mentioned, something has to come from the machine learning world, in the sense of they are also, I assuming, trying to solve the problem that the underlying data evolves, and how can you don't want to retrain a model from scratch. You have models that you can adjust so that you do not have to completely retrain it from scratch. And so you would need machine learning expertise also to find these kind of machine learning models, and then you can put them in, for example, into these learned indexes.
Okay. But you also hinted at there's multiple models, or like different sections of
well, the research that I'm knowing about, they try different models, like linear regression models are the most common. Why? Because you want the inference in the nodes to be fast. So the researchers tries, I can put a deep learning model in it. So the deep learning model is great, it's very accurate, but first of all, it needs a lot more data to be trained. And second, once you put a data in and you do inference, it actually takes, depending on the size of the model, quite long. Mona has experience with this. The inference is not a fast process. So now in a tree, you have thousands of requests that says, okay, I have the value 5. What is the next child? You want to do this inference fast. So if you have a linear regression model, that goes very fast because it's a linear regression, right? So it's like 2 multiplications and a subtraction or something like that to kind of get to the result. So you want to have models there where inference is fast.
Got it. Yue has a question if you will make the slides available.
Yeah, sure. I can give it. I can send it to you.
Cool.
Any further questions? Doesn't have to be explicitly the talk. Maybe you want to just know something about I want to do some research in systems. How do I best start it, or anything like that?
Yeah, I'm sure if there's undergrads present, they'd love to
get
an answer to those kind of questions.
Yeah, I was gonna say the same. I've had quite a few conversations with undergrads lately. I think that would be an interesting perspective if you wouldn't mind sharing.
Yeah, for sure. I mean, you feel also free. You can forward it to the undergraduate society, can let them know. I assume you might have done it already, to the links for the ready talks, right? And they might find them interesting.
And I did my undergrad research project with Dr. Kemme, and I really, really enjoyed my time. So if I can vouch for it.
Thanks. Justine, I hadn't seen you change later. Thanks for this nice comment.
I do have a question, but it's very, very vague, and it will show also a little bit my lack of understanding of database. I never took an actual class on it. So I do a lot of work with graph representation learning. Is there...
With what? I didn't hear that.
With the graph representation learning. Yes. So, normally one of the ways to look at that as a difference from traditional ML is a little bit how the information is stored, and how it's, it's a little bit, so is there different ways that databases can help model this? And like with the tool that you're talking that you do with Ready, like, is that something that's taken into account, or is this something that's not even an issue? Like it's very easily transferable.
So it's not work that we have been doing in our lab, but there's definitely systems people looking into how to support graph-based machine learning algorithms. The graph representation definitely plays a role in, for example, you explore neighborhoods in these graph-based deep learning models to build aggregate information. These functionality has definitely been there's a lot of, they exist graph-based database systems. If you look at Facebook, Facebook's data is basically a graph, a social network graph, where they do a lot of aggregation, distributed graph processing. And there's a lot of expertise coming there and looking in. Here, the challenge is to understand the machine learning. So the machine learning people came, okay, I represent this as a graph. And now what I build is I build these aggregates over these neighborhoods. And then I learn as far as I understand, in a manner, building these aggregates, building weights, building again aggregates, and doing this in kind of a mixed manner. A challenge is to understand really the algorithms, because they seem to be a lot more complex than the algorithms that were needed, the functions that were developed by the distributed systems community, for example, to do graph processing on social media graphs. Mm-hmm. But once this is in place, I think there has been already a lot of work. So for example, work that goes on the GPU, these graph-based models do not work so well. And in my understanding, it's harder because you don't have that great a data parallelism that you have with other ones. Okay, every record you do something, and therefore it works really well on the GPU. And these graph-based models are a lot more complex. They are often also interleave with other deep learning models. It might be only your embedding layer that follows the graph, and then there's other layers around. So how do you distribute the task? And I have definitely seen work like looks into it, but currently it falls into this. I had here actually the slide at the very end where I mentioned it. You have graph-based deep learning models with sparse embeddings, where you translate this, and now you want to build a workflow. How can you best do this? They really look at one particular algorithm, and then they try to optimize this algorithm and distribute the work over the GPU and CPU to perform it. So there's definitely work around, but it's basically happening right now I would say in the last 2 to 3 years.
Yeah. Because all I've really seen is sampling is one way to go around it a little bit to
yes.
help limit how much it's asking of the computer. And then if not, doing einsums, which for those people who work with them are very annoying and hard to visualize, but they're very powerful because they really help parallelize stuff. Well, for computers that is meant to very GPU heavy. Okay, that's really cool. Yeah.
But what you find, for example, work, you have a data structure like a graph there, and now you want to put, for example, some information into a cache, you will find solutions. Okay, how do I represent the graph now so that it is cache efficient, so that it can, for example, fit into a GPU cache? Mm-hmm. And so what the machine learning people right now do is they program the thing in Python, and then they put it into TensorFlow, and then they try to hope for a good compilation. And so what you have is you have compiler optimization there. But for example, the systems community now really looks at the higher level structures of it. And so they don't take your program, they take your data structures and the higher level operations on it and try to map it to these data structures that we are familiar on with systems. Is it a hash table? Is it a really using the register lines of your GPU, et cetera, for the most relevant ones? They really look at this level, which compilers would usually not be able to do.
Mm-hmm, mm-hmm. Thank you.
Yeah, on the subject of compiling, I have a question about the ADA system.
Yeah.
So is the Python interpreter doing some kind of compiling to SQL queries to bridge that connection?
Yes. So what you have is if you have worked with pandas and you will find so you have this data frame, and then when you call something, it's data frame dot multiply or whatever. And so the pandas also allows you relational operations dot filter. And filter is nothing else than the where clause and the select statement. So what AIDA does, it hasn't used the pandas language, but a very similar one. And when it takes these requests and it translates them internally into SQL, and then sends the SQL to the engine. It does this automatically, the translation. But what it does, when you write in pandas filter, and then you write project, and then you do a join or whatever, pandas will execute one statement after the other. In AIDA, it will just all store them. And then when you say, now I want to see the data, then it takes them all together and translates them into one SQL query, which optimizes the process a lot. So it executes these SQL queries not only faster because it's a database engine that has the optimized data structures, but also because it agglomerates all these requests and puts it in one big SQL query. And then obviously it becomes faster than if you do one after the other. And for each of them, you have an intermediate result.
Super cool.
Yeah, it's super cool. But that's Joseph's work there. He has put really quite a lot of time in doing that.
Does it scale up well? Or like, because to me it seemed like
we are looking into scaling issues. I think one challenge is Python. It's a
Python itself, right?
Python is not your greatest language here to really do. Parallelization is hard, multi-threading is hard, all these things, right? So you know, you have these who translate everything into C because then you can optimize it. But we use Python because everything comes in Python, and it's not the greatest language, that's for sure. So right now we don't translate because that would be a lot of effort. We had I had a different project with a student with a former Laurie Hendren together. He graduated a year ago, and he did something, but only for SQL, that he combined it and did specific query optimization using compiler techniques. And he looked a little bit into also doing this for data analytics, like you have a data analytics task, not written in Python, he used MATLAB, and you have this combined, and then he would use a compiler optimization over that.
Yeah, because I know Python has like the global interpreter lock, so really it's like only single threaded, right?
Yeah, we are right now playing with a multi-threaded one, and you can do it for certain amounts, but it seems to become a risky endeavor to run things in parallel. That's for sure.
I have a little bit of a question. You talked about like depending on like certain scheduling, like for example, if you schedule on a GPU or in a CPU, like performance would be different, like certain workloads. So I work with Oana. I'm a master's student of hers, and I don't know if you have any maybe recommendations on publications or resources on like how to go about systematically measuring performance of like these like how do different like scheduled workloads perform? Because I know that there might be caveats on like reproducibility of results when measuring performance, for example.
Absolutely, and I think it's a huge challenge here because it's very low level. In particular, when you go into the GPU, then it depends highly on which GPU you're working on, and each of them is slightly different. And so really understanding it is a challenge. So what I read in the literature, typically in systems related research, people, at least to the program committee, when they submit their papers, submit the source code. But then really getting this to run and testing it out, not a lot of people do it because it's really hard work. In the papers themselves, I haven't actually seen good descriptions of that, of how exactly they measure it, etc. We have I have right now an undergraduate student who explores a little bit the scheduling, and we are getting slowly familiar of how we can do measurements. I'm happy that we once meet up all together and exchange experiences of how to do proper measurements, particularly in the relationship CPU and GPU, because it's non-trivial.
Okay.
I'm very happy to share also experiences with you. We have looked a little bit into the research literature of how to exactly do it, but we really haven't found anything that would help us much particular to do the exact measurements.
Okay, interesting. Well, thanks.
But if you would like, you know, I'm happy to invite you to one of the meetings, and you can tell your problems, and the people who have worked with the GPU can give you feedback of what they have been doing.
Sure. Well, I'm currently working on more like IO, disk-based IO, but like I would think that maybe performance measurement, like maybe more of a general area of research. And this is why I asked. But yeah, thanks.
But what kind of measurements are we talking about precisely? Like, because you can use the NVIDIA SMI tool, you know, it gives you like % of the GPU's processor that's being used, etc., the amount of memory it's using. But
yes,
what kind of deeper data could you need?
Well, they are kind of tricky things if you have several GPUs, how to know which one is actually exactly used by each of them, the times when they are used. So for example, if you want to have the interaction with this between the CPU and GPU, are there idle times on the GPU because the GPU is waiting for the CPU? So you need the analysis over time, which is a challenging thing. An important aspect of all that is that you're not intrusive. So if you measure too much, then it falsifies your result because the profiling itself can use a lot of resources. So that is a challenge with that too. So often we try to be quite in a first step to be not very intrusive if you want to measure CPU utilization, etc. But yes, we use just the standard tools that are available and try them out and see how reliable they are.
Cool.
Okay, well, I want to thank all of you being here. It has been a pleasure speaking to you. And if you have any further questions, feel free to reach out.
Yeah, thank you very much for coming.
Thank you.
Thank you.
Okay, thanks, and all success with society and all your parties. Once the school does parties again, I mean, you might know I was director for a while, and we had actually very nice parties together with the graduate students, but nothing has happened in the last 2 years. So I hope the new director will restart that at least maybe one thing this semester. Let's hope. Bugger him if he doesn't. Write to him.
Crossed.
And the school also supported, you know, so we were paying stuff. The school was paying stuff. So you should not be afraid to ask them to pitch in. The school has a budget for parties, not parties, but you know, events where it sponsors food, etc. And the budget is full because nothing has happened.
Yeah.
We have a meeting next week, so
Okay. Perfect.
I'll make sure to ask Matthew Blanchette.
Yeah. Okay, cool. Excellent. Okay. Thanks a lot for being there.
Yeah.
Thank you.
Have a good day,
Okay.
everyone.
Bye-bye.
Bye.
Yeah,
Bye.
bye.